show of hands, who's first time here? Oh, spattering of you. Good, good. So we hope that you will enjoy the experience and come back. So, first of all, a few housekeeping things. If there is a fire alarm, we're not expecting one, but if an alarm does go off, please leave through the door by which you came and congregate round in front of Burlington Burlington Gardens. My name's Elizabeth Rollinson. I'm the exec sec here. Normally, you would expect to see Leanne, but of course today she is our speaker. So it is my great pleasure to introduce Leanne to you. And so for those of you who do come regularly, you will have seen Leanne. And she's been in role now for a little over a year, and she's fulfilling that role with tremendous enthusiasm and energy and innovation. So we are absolutely delighted to have her in that role. She also has an outstanding academic record. She was awarded her Masters in Science in Chemistry by Bristol University in 2013 with first-class honours. She then went on to do her PhD jointly between the University of Bristol and the Natural History Museum in London on the effects of environmental change on unattached corallines. Leanne's already published widely as a senior author on her research and has given a number of well-received presentations for which she's been awarded. She's very keen to engage with the public, and her role at the Society allows her to do that while keeping a finger in academic research by working a day a week at the Natural History Museum, where her current focus is on coralline taxonomy. So Leanne's talk today is entitled "The Future of Coralline Algae."
Thank you very much, Elizabeth. It's a bit weird being on this side of things. Is that a bit too loud, or is that okay? Yes? Okay. So full disclaimer, I haven't actually done a proper presentation on my PhD since I finished, which was about 18 months ago, so I may be a bit rusty, but we'll go anyway. First of all, I wanted to talk about the stuff down here. So we've got a few species of coralline algae. So coralline algae is a red seaweed that calcifies, and then we've also got green seaweed as well that calcifies. So it's not technically coralline algae, but it's a calcified seaweed. These are from Linnaeus' collections himself, and then we've also got a book here by John Ellis when he did a whole study of the corallines around the UK. And I've got one page open, and it's got Linnaeus' annotations in it as well. So after the talk, you can come and have a look at those. So yes, as Elizabeth said, I did my PhD partly between Bristol and the Natural History Museum, and I looked at the effect of climate change on coralline algae. So what is coralline algae? And this is when it turned on. There we go. So coralline algae is a type of red seaweed that calcifies within its cell walls. We can see the calcite here, giving it this hard, chalky-like appearance. And so we have different growth forms. We have the articulated corallines. So there is one down here, Corallina. They calcify. You've got sections that calcify and sections of non-calcifying material, which gives it this kind of tree-like appearance. And you find them on the fringes all around the UK. So Corallina officinalis is the major one in the UK. And then we also have a crustose form. The crustose form is where it's all fully calcified. And I don't know if you've been on the rock pools and you see those pink purpley splashes in the pools, that's coralline algae. And then my favorite, so some of these crustose forms can actually produce these branches, and these branches can break off and they continue to grow. So you have these unattached corallines, rhodoliths, smell. So that's what I kind of looked at. With rhodoliths and mel, the names slightly mean different things. So rhodoliths are centered on something like a nucleus, so like a stone, and it grows around it, whereas mel is technically completely unattached, so it's a branch that's kind of grown and broken up. For the issues, they provide the same ecosystem function, they provide the same habitats, and people have gotten very confused over the years as to what exactly is a rhodolith, is a mel. So for the purpose of this talk, I will just say rhodoliths, but I do mean all unattached corallines. So the importance of rhodoliths. So these unattached corallines, these rhodoliths, they live on the bed and they interlock together, creating these vast habitats. And they have all these like little nooks and crannies and spaces which are ideal homes to a wide range of organisms. So we can see these brittle stars here. But they're also a nursery ground to commercially farmed scallops. So if you like your seafood, then these organisms are important. And we also see, they've also seen like baby cod and baby pollock living among the beds, different types of seaweeds. And in the beds in Falmouth, we actually have a male specialist, a certain type of seaweed that actually only is found on the male beds in Falmouth and isn't found anywhere else. So they also have a global distribution. So here I'm just showing different species around the North Atlantic, but you do find them from the high latitudes, polar latitudes, all the way to tropical, and you can find them in the intertidal pools, all the way to about 150 meters deep. And because of that, they are one of the major carbonate producers. So there is the world's largest rhodolith bed is off the coast of Brazil on the Abrolhos Shelf, and it contributes 5% of the total carbonate budget. So they're pretty important stuff. And because of that, there are certain threats to rhodoliths. So what we have here is that they are ecologically fragile, they are highly sensitive to their environment. And because of their really slow growth rates, so on average they grow about 1 millimetre per year, they're seen as a non-renewable source. So here, they're susceptible to things like pollution. So there's certain beds in Brittany where you've lost them from like the major sewage outflows. And then scallop dredging, as I said earlier, they're a nursery ground for scallops. Scallop dredging completely decimates them. So they kind of break up the lattice and they bring up all the silt and sediment off the bed, and that kind of causes them to smothers them, and they suffocate because they need to have the gaseous exchange and die. So they're actually protected. So there's three species in the UK that's protected under UK and EU law. And then the other thing is fish farming. So we've got here on the west coast of Scotland, this is a pristine bed, and you can see the lovely pink colours and the starfish. And then this is a bed that was found underneath a salmon fish farm. So all of the stuff from the farm that basically comes and smothers the bed, and it's basically turned to gravel. And yes, you do have a few organisms living in there, but it's not the same as this lovely pristine bed. So they're already dealing with human pressures such as pollution, scallop dredging, well that's been banned now, and fish farms. So the other challenges they have to deal with now is climate change. So what exactly is happening with climate change? So we have increase in carbon dioxide in the atmosphere, which we know leads to warming, and we also see this warming in the ocean. So this graph here kind of shows the warming from 1960 to the early noughties. And what you can see is around the UK, it's the temperatures getting hotter. And what this over here represents is the mean number of species of zooplankton, a warm temperate species. So what we're seeing is that with the increase in temperatures, the warm temperate species are moving further north. Their ideal habitats are changing, and so warming is changing their distribution. With warming, we get thermal expansion of the waters, we get melting of the ice caps, so sea levels are predicted to rise as well, and they have already risen. And as well with sea level rising, with the increase in energy that we get in the oceans through temperature, we're predicted to see more storms, more intense storms, and more frequent storms. So what impact will this all have on coastal ecosystems? So the other big CO2 problem is ocean acidification. This is where dissolved carbon dioxide changes the chemistry of the ocean. It makes it more acidic. You're forming this weakly dissociating acid, which will react with ions in the water, and it's lowering the pH. So we can see here increase in CO2 in the atmosphere, corresponding to the same increase in the ocean, and then this is a decrease in pH. So, this is my poor diagram trying to explain that a little bit more. But yeah, so it's a similar thing there. So what impact will this have on organisms? So a lower pH makes it harder for calcifying organisms to build their shells, to build their skeletons. So what is predicted is that we'll see a shift from calcifying species to non-calcifying species. So this is taken from Brody et al. In 2014. They looked at the future of flora in the Northeast Atlantic. And so what you can see is in the Arctic, in present day, we've got our merle, we've got these epiphytes, so these are things that grow on other things and they calcify as well. And then when we move to a future high CO2 condition, we see that we've lost the male, we've lost these calcareous epiphytes. We have more diatoms, more seagrasses, more fleshy algae. We're moving away from a calcified environment to a more dominated fleshy algae environment. So I've kind of talked a bit about other organisms, and this talk is about coralline algae. So what about rhodoliths? So what we see with temperature is these rhodoliths actually do really cool things like tree rings. They kind of show growth rates. And what we can see is that so they have seasonal growth. The growth in the summer is different to the growth in the winter. In the summer, where it's warmer temperatures, they grow a bit faster. And through that, they have these larger cells with these thinner cell walls. As they're growing faster, they are unable to deposit as much calcite into their cell walls as they would if they had a slower growth rate. So you see this difference where these larger cells with thinner cell walls compared to the winter growth. And you can see with this species, there's hardly any winter growth at all, where it's smaller cells and larger, thicker cell walls. So you can actually use this to calculate how old they are, because each of these bands is a year's growth. And then also, with calcium carbonate, the actual calcium carbonate form that they produce is called high magnesium calcite. So they incorporate a lot of magnesium into their skeleton as well. And we can actually measure that as well. So here we've got the warmer colours represent areas of high magnesium compared to the cooler colours. And this is also, so they incorporate more magnesium in the warmer temperatures compared to the colder winter months. So we can also use that to look at growth rates as well. So that's the role of temperature. When we look at the role of ocean acidification on coralline algae, what we see here, so this is from my work with my colleague, Federica Ragazzola. She gave a talk earlier on in the year about different types of species, but also coralline algae. And so this is just kind of a diagram of the cellular structure. You can see the, oh, gone the wrong way. You can see the internal cells here is similar to this here. So she grew rhodoliths, coralline algae, under current CO2 conditions and future CO2 conditions. And so you can see the cellular growth here. And then under future CO2 conditions, where a higher increase in CO2, you can see that the cells are now larger and the walls are thinner. And she also measured differences in the magnesium concentration as well in the calcite. So what we can see, so but keep going the wrong way with this thing. So here I showed you a kind of temperature control on the magnesium incorporation. Here you can also see that there is biological controls. So around the cell, when they're growing, you can see there's a high increase of magnesium there, and then they don't incorporate so much, and then they incorporate more magnesium depending on the stage of calcification that they're currently doing. If we look at high CO2, that control is gone. There's something there that's stopping them from being able to control the actual amount of magnesium they incorporate, and also overall, the amount of magnesium is lower. So that's kind of showing what temperature and ocean acidification is doing to the internal structure of coralline algae and the material and the mineral chemistry. My interest in my PhD was more about how do these changes actually affect their structural integrity? How does it affect their ability to maintain that 3D structure that allows them to maintain the habitats that they form? So we need to go back to Feder's models, because these are actually finite element models. So finite element analysis is an engineering package. It's used to assess stress and strain build-up in a model. It was originally derived in engineering to look at assessing the structural integrity of bridges and planes. And so now it's being used to look at biting forces in dinosaur skulls and look at the evolution of bird flight. Like, it's many, many applications. And so here I use it to assess the structural integrity, looking at these models and how changes in cellular structure affects the strength. So, So initially, as I said, the increase in CO2 caused these larger cells with thinner cell walls. What you need to know about this model is that the warmer colours indicate areas of high stress, and the cooler colours indicate areas of low stress. So what we can see here is that with larger cells and thinner cell walls, there's more stress in that model. The model is more prone to fracture. These are simple 2D models, though. So when we started, we had no idea if it actually really represented the internal skeleton of a coralline algae model, specimen. So what initially we did was we tried to increase the complexity of these models to try and get it as close to a more realistic model as possible. So initially we went to 3D, so we just expanded it back to 3D. And then as coralline algae grow, they grow in individual cells. So we added compartments, which gave us this individual cell model. And then this is the true model. So this model was derived from CT scanning, and it's basically what it looks like inside. And so we compared all three, and as you can see, you've got all these areas of high stress on these cellular walls here, which isn't seen in this model or in this model. It's a bit difficult with these two, but we have gone through the whole model as cross-sections, and it basically looks exactly the same as it does inside as it does on the front. These models have similar stress distributions, and the actual overall average stress was exactly the same between these two. And what was really interesting, which I was surprised it happened, was the amount of calcite that we had compared to open space was exactly the same. And so I was like, oh, wow, that's even better, that's handy. So it meant that this model, which took hardly any time to make, you had to measure a few cells and you could create that model, was so much easier to do than this one. This one required us going to Zurich, because if you can see the scale here is 5 micrometers, so we needed a CT scanner that could scan on the nanoscale. So it required going to Zurich, paying for scanning time. The time taken to actually create that model was ridiculous. It was so long to process, and it kept on crashing. It was a nightmare. So when we found this model that was like you could do in 20 minutes, it meant that you could now test a whole load of questions, which makes my life easier and makes my thesis look better. So we went back to Feder's original question about how does ocean acidification affect the structural integrity, and we redid the test. And so what we can see is, yes, there is still an increase in stress in the model. So the model under future CO2 conditions is more prone to breakage, but the difference between the two isn't as drastic as the 2D model suggested. So there's a bit of hope. So we looked at this, we looked at what initially was done, and then we decided to look at different species. So I wanted to see if certain species were forming weaker skeletons than others. So these were my sites. So I had a site down in Falmouth, and then 2 sites up in the north. So we had Oban on the west coast, and then we had Berwick-on-Tweed on the east coast. In the end, we didn't actually find any specimens there, which is the reason we chose these sites, first I should say, is because we had material in the Natural History Museum from the early 1900s. So it was about looking for those material and looking for comparison sites later. What was interesting about these 2 sites is that we had material from there, and then in the end it took us a long time to find actually where the bed was in Oban, but we could not find it in Berwick. So obviously there's distribution changes already going on in 100 years. So yeah, so we have these warm temperate species down in Falmouth, Phymatolithrium calcareum and Lithophamnium coralloides, and then up in the north we had Lithophamnium glaciala and Lithophamnium erinaceum. So these are our cold temperate species, and these are warm temperate species. And so next I'm going to show you a video of, this was in Falmouth when we were collecting some samples. At this time I couldn't dive, so I didn't actually dive for the specimens. You can see me on the boat, but I had some divers dive for me. We were very lucky with the weather. It was a beautiful day. So I'll just show you a bit of the diving. And so you can just see, this is, so this is actually one of the healthy beds in Falmouth. In the harbour, there's an area on the other side called St Maur's Bank, and that is where it used to be the one live merle bed bank there. The rest of the harbour is full of dead merle, but they have found more sites around the coast since I started my PhD. But yeah, so this is what it kind of looks like down there. So you've got like a mixture of lots of different species and seaweeds and stuff. So yeah, let's move on. So yeah, so we've got here, so these are our warm temperate species. This is what it looks like inside the cellular structure. And then, cold temperate species here and our warm temperate species here. You can see the differences in the cellular structure. I looked at summer growth because there was a lot more of it and it was easier to measure compared to the winter growth. So we're all comparing summer growths at the same bands because they were all collected at the same time. So these are what the models appeared like. And then when we run our finite element analysis, you can see that the cold temperate species, there's less stress in the model compared to the warm temperate species, which makes sense. These are much larger with thinner cell walls. There's a lot more calcite here. It kind of makes sense that this model would be more prone to stress and more prone to breakage. What I found was when I was doing the analysis and I would break off branches for analysis, it was much easier to break these species, break off a branch than it was those anyway. So it kind of is adding up. Well, yeah, so you're doing okay at the moment. So structural integrity between different species. So the colder temperate species are forming, the warmer temperate species are forming weaker skeletons than our colder temperate counterparts. So we also, as I said earlier, I had a whole lot of collections from the early 1900s as well. We also looked at through time. So this is, in the end, I could only do it on the warm temperate species because the beds were still there. We had from early 1900s, we had from like 1970s, 80s, and then this was the 2010s. And we looked at comparing the cellular structure. I don't know if you can see any differences, but I couldn't really see much differences in the cellular structure there. When we did all the measurements, they did come back significantly different. But when you actually ran the models, it wasn't large enough to really cause any difference in the stress or strain buildup. So it looks as if over a 100-year period, yes, there's changes in the cellular structure, but it's not enough to really affect the structural integrity. So after that, we decided to look at the future again. With all of these models, we were working on previous work where they'd used these loads that we had no idea where they came from. So we weren't sure. It's fine here because these are all comparison models, so you're using like for like. But when you come to actually trying to assess the differences in storm surges, so an increase in load, we kind of need to know exactly what they're experiencing in the water at the moment. So it meant that I had to go to California for 3 months. It's a hard life. And so I got to go to California and spend a couple of months working on trying to calculate the actual drag forces. So drag is the major the force that marine organisms experience in the water. So first of all, through that, I first had to calculate breakage stresses. So this is the force required to actually break a piece of coralline algae. So I did this in the first week I was there, and I turned up at this big old massive machine, and it's actually called the algae torture rack. And so you'll see what it does. So this is how we calculated breakage stresses. You can just about hear it as it's getting closer. Yeah, it's not really nice for a bit of algae, is it? But yeah, so I got to do that over and over again. And then we also, so this is how I calculated drag. So normally when you calculate drag, you have this big old tank, it's called a flume, and you attach a piece of seaweed called the holdfast, and then you've got this motion of the water coming through, and you calculate drag that way. It's a bit difficult with these things because they're not attached, so it's hard to measure the drag force that way. So what we had to do was kind of flip it. So what you do is you drop a piece of seaweed, you drop it into the column, and you calculate how quickly it moves between an area of known length. So this is me dropping my seaweed into the column. The strings are there because I haven't got a video here, but I do have it on my phone if you wanted to see it. The strings are there because I had to create a little algae elevator to bring it back up. So that was quite fun. Yeah, so it was a lot of makeshift equipment in this lab, which was really cool. I got to play with Lego as well on one section, but I won't show you that. So yes, that's us calculating drag. So through that, we were able to calculate what kind of forces they experience currently in the water, and then we could calculate, knowing that, so it was knowing what the kind of water velocities and water speeds would be currently, and then what we expect them to be under an extreme storm, and then we could calculate different loads. So this is, the wrong way. So this is what it was under current conditions, and this is under future conditions. So now this looks like it's less, but if you look at the scale is much higher. So under stormier conditions, they're experiencing more stress, more strain, more prone to breakage, and the average stresses that came out of these future conditions actually exceeded our experimental breakage stresses. Now, it doesn't mean that under a stormier condition, the loads are so strong that they'll just break like instantly, but it does mean that there is more cause for concern because they are going to be under more pressure. So to kind of sum up that, so my thesis kind of saw that the warm temperate species are forming weaker skeletons compared to their cold temperate counterparts. However, if you're looking at just ocean acidification and temperature on the cellular structure, over 100 years, you're not really seeing enough change to cause a significant difference in the structural integrity, which actually kind of coincides with this experiment here, because the data I showed you was just the first 3 months. When they went back to the specimens that they were growing in 10 months, they'd actually gone back to this. So they'd decreased their growth rate to be able to thicken up their cell walls and go back to what they prefer. So they're obviously able to reallocate their energy to deal with different changes if it's in slow enough time. But future stormier conditions, which are predicted, will cause them to be under more intense pressure than they currently are, which is going to make it difficult. If they're already having to reallocate their energy to deal with other pressures like temperature, ocean acidification, or other human pressures like pollution and aquaculture, then they've now got another pressure in the future stormier conditions. So what we probably would see is they're moving, they're more mobile on the seabeds, they're more likely to collide with each other and more collisions, and therefore are more likely to break. So it's going to change the nature of the beds that they form. And in doing so, they're going to form smaller fragments. And these smaller fragments, as in the same way with scallop dredging, they're going to be more susceptible to smothering on the seabed by silt. And in changing the nature of the fragments, you're changing their 3D structure and you're changing the habitat that they can form. So the same organisms won't be able to actually live in those beds. It's going to be more difficult for the warm temperate species because they're already weaker. They're already producing less calcite than their cold temperate counterparts. So it's a bit doom and gloom, but you're probably going to see more of these beds. And even just doing my PhD in the last 3-4 years, I remember seeing in the literature about this bed up in Loch Fyne, and over like the course of like 5 years, it disappeared. And so, we're basically seeing that we're predicting that you're going to get more of these kind of gravels, these less pristine beds, and you'll probably see less of these. And it's also you're going to see a shift as well, because as the temperatures get warmer, species will be moving further north. So, yeah. That was my thesis. I didn't talk about the mineral chemistry side of things because it kind of gives a similar sort of results, but if you want to discuss it a bit more, and I'm happy to answer any questions. And I just want to say I want to thank my supervisors and everyone who helped me on the project, and also NERC, the Natural England Research Council, because they funded my PhD. Thank you.